Okay, so thanks, Miguel, and thanks to the organizers, Cameron and Rene, for carrying on with these Swampland seminars. And I'm very happy to be here and to talk about this work, which is actually joint work with Miguel and Julian, who's another postdoc here. Okay, so let me provide some motivation before we start. So we're all familiar with the Swampland program here. This is the Swampland seminar after all. And so in this program, we use string theory as a laboratory to check which effective field theories can and cannot be embedded into a UV theory of quantum gravity. So hopefully this notion is familiar. And these statements that we make that differentiate these two classes of EFTs are called the Swampland conjectures. Okay, and one thing that's really cool about these conjectures is that we can actually use them to learn more about our world. Okay.
Yeah, we're good. You keep going.
Yeah, so can everyone hear me? So I'm facing the other direction, but the mic is behind me. So
Let me just record.
Good.
There we go.
Okay. Yeah. So one very interesting aspect of this program, as I was saying, is that we can use it to learn non-trivial things about our real world, and in particular, there are very few papers that have tried to connect the swampland to matter content in our universe, either today or in the past. And this is the question that we want to ask today, and we're going to explore this. So what can the swampland say about the matter content of our universe? Good. So with this motivation, this will be the outline of my talk. There are two parts, and there are two parts. In each part, I will first introduce some swampland principle, and then I will apply it to our universe, and then we can see what we can learn from those. So, like I said, the dictation, this organization is dictated by which principle is at play, and there are very few here. In the first part, we'll talk about the weak gravity conjecture and Festina Lente, which are related constraints, and in part two, I will talk about photon masses. Okay, and then we'll look at various applications. All right. So please interrupt me if there are any questions. Yeah, I hope this is more of a discussion than just a talk. All right. So let's start with part one. So first, let's quickly review the weak gravity conjecture. So this is one of the oldest conjectures in the Swampland program, and there's some precise statement that relates the charge to mass ratio of particles to the charge to mass ratio of large extremal black holes. But in practice, what this means is that in all spectra that we get from string theory, there exists a particle whose mass is lower than its charge in Planck units. And of course, so this has been checked in all examples that we know, and it's satisfied in all string theory examples, and it also holds in our world. For example, the electron satisfies this bound with a lot of room to spare. There's also a nice connection with black hole decay in that Q bigger than M is exactly the kinematic condition that we need so that extremal black holes can decay while remaining sub-extremal. And right. So Festina Lente uses the same principle and extends this to the Sitter space. So it extends this to charged black holes in the Sitter space. So our discussion so far has been about black holes in flat space, where there is an extremality bound that I'm showing here by this line. So this is the mass of the black hole in flat space, and this is the charge of the black hole. And in flat space, black holes with charge bigger than mass, they have naked singularities and are pathological. So we say these are bad black holes. But those that are in this region that have mass bigger than charge are okay. Now, in the Sitter space, things are qualitatively different because there is a de Sitter horizon. And so if there's a black hole in the Sitter space, and there's also a black hole horizon, and as we make the black hole heavier, the horizon of the black hole increases in size, and eventually it will coincide with the de Sitter horizon. These black holes are special, and they're called Naria black holes. And they're actually the largest black holes that can fit in the Sitter space. So this concept doesn't actually exist in flat space. if we do this more carefully, then the extremality region in the sitter space then looks like this. It looks like a shark fin. So there is qualitatively there's a bound on how massive black holes can be. And there's the usual extremality bound that we're used to in flat space. And everything inside the shark fin is sub-extremal, whereas black holes outside the shark fin are super-extremal. And we believe that they're pathological in the same way that black holes, that super-extremal black holes in flat space are. Now, these Navier black holes are interesting because they are on the verge of becoming super-extremal. In particular, if our theory contains charged particles that are too light, then these black holes can decay and they can leave the extremality region. They can decay outside this extremality region. In order to forbid this decay channel, we must ensure that all particles in the sitter have a mass that's bounded below by this quantity, which is the gauge coupling times m Planck times h, and h here is the Hubble expansion rate of the sitter space. So this is Festina Lente. So every particle in the sitter satisfies this inequality. It has a mass that's bounded below. Okay, quick recap. So that was a very quick summary of weak gravity and Festina Lente. But so the important parts to remember is that the weak gravity conjecture says that there exists a particle with charge greater than mass. And Festina Lente bound says that all particles in the sitter have mass squared bigger than m Planck h times the gauge coupling. Okay, so any questions so far? What we do next, we'll just be applying this to various models. Here or on Zoom.
So can I ask it?
Yeah.
Should I? Is this to speak up?
Yeah, speak up.
So the Festina Lente bound where you have Hubble appearing, I can imagine that Hubble is not constant in the history of the universe. So does it have any implications with that? Because the bounds.
Yeah. So Hubble here can be changing as long as it's changing slowly enough in a way that can be quantified.
Something which was allowed will not be allowed and vice versa.
So if Hubble's changing fast enough, then it doesn't look like a sitter, and these particles will then be allowed. So particles that violate this will be allowed. If Hubble's changing fast enough, yeah.
It's not a sitter.
Right. If Hubble's changing slowly enough, then it's still the sitter, and then we can apply this bound. Any other questions? Just two things to remember is just charge bigger than mass, and then mass squared bigger than m Planck. Okay, so let's move on to the applications. So the first application is the simplest, and it's applying these inequalities to darkly charged particles. So of course, dark matter is very well motivated. We have a lot of evidence for the existence of dark matter, and we also know that it interacts very weakly with us and with itself. And this here is an image that illustrates these 2 points. So the purple haze here is the dark matter halo, and the pink haze here is the gas. And the interpretation of this picture is that it's the collision of 2 galaxies. The gas gets stopped here in the middle, but the dark matter halos just pass through each other because of the weak interaction. So you can imagine that this puts some upper bound on the self-interaction of dark matter, and we'll use this upper bound later. So the first one, so nonetheless, even though dark matter interacts weakly with itself, dark matter interactions are well motivated, and they can help to solve certain astrophysical problems on small scales. Okay, so they have been considered a lot in the literature because of this. The first model that we'll look at is very simple. So we'll suppose that there's a dark photon. We'll call it A prime, and it has a gauge coupling G prime. Now, by the weak gravity conjecture, there must exist a dark electron that we'll call it chi, and its mass will be m chi. We can then just apply Festina Lente to this particle and this gauge coupling, and we get an upper bound on the gauge coupling. Okay, so this is just a rearranging of the Festina Lente inequality. If we plot this upper bound, it rules out a region in parameter space that looks like this. So on the x-axis here, I'm showing the mass of the dark electron, and on the y-axis, this is the gauge coupling of the dark U1, and everything with the gauge coupling above this line is ruled out by this inequality. So at low masses, this begins to compete with astrophysical constraints. This, for example, here is a constraint from dark matter self interactions, which are very similar to the bullet cluster merger collision that I showed you. So I told you these collisions, they put upper bounds on how strongly interacting dark matter can be with itself, and these bounds are basically this line. One thing though that this line has to assume is that all of dark matter is actually composed of this particle and chi, of this particle chi, and yeah, so otherwise this bound is evaded. For instance, chi can exist in the spectrum but may not be populated in our universe, just like muons, for example, exist in the spectrum but there are no muons around that form an abundance. So our bound here does not have to assume anything about the abundance of this chi particle. We didn't even have to know anything about galaxy mergers, in fact. So this is one thing, and there's another thing that we don't make any assumption about the interaction of this of the dark sector with our sector. So yeah, so this is the first bound of its type, because usually in order to constrain the dark sector, you have to assume how it interacts with us, and then we can only see it through that interaction. But here we don't have to assume that there's any interaction between the dark sector and Mars. So this is, in some sense, much more general. Yeah, any questions about this? Good. Okay, let's add one complication to our model. So in the first case, in the first scenario, we just discussed our photon and dark photon, and what we can do now is add a mixing between the two photons, parameterized by this little parameter epsilon. And so this mixing operator is a dimension 4 operator. So even though it might be generated at some high energy, it can still remain important in the low energy theory. As we can see here, then this kinetic term is no longer diagonal, but we can diagonalize it again, so we can redefine our basis. And once we do that, then the dark electron chi, which was charged under F prime, will now get a Miller charge under R U1. So yeah, under the U1 of electromagnetism. So the charge vectors will look something like this. So our electron will be charged under RU1 only, and it has 0 charge under the dark U1. The dark electron will have a charge under RU1 that's proportional to epsilon, so it's epsilon G prime, and will of course still be charged under its own U1. We can again apply Festina Lente to this setup, and in the presence of multiple U1s, what Festina Lente says is that m squared is bigger than the norm of the charge vector. So it ends up giving the same bound, G prime less than m chi over m prime each. Okay, so like I said on the previous slide, the dark electron now has an electric charge. It's proportional to epsilon, and its value is epsilon G prime. So this in particular is less than G prime because epsilon is smaller than 1. And so here we're throwing out some information because we're just we're being agnostic about how small or large epsilon can be. And then this inequality we found from Festina Lente will then give us an upper bound on the charge of the dark electron. Okay, usually in literature this is expressed in terms of the electron charge, and so it ends up being some bound like this. So the charge of the dark electron is less than its mass, and we can again plot this on the plane of the mass of the dark electron versus its electric charge under RU1 this time. So this is the electric charge under RU1, and this is the mass of the dark electron. And we can again rule out some region of parameter space that is up here. So again, some things to mention. This is comparative at low masses with lab experiments or observations, and there's no assumption on the abundance of this dark electron again. So we didn't have this dark electron didn't have to exist. There does not have to be a thermal abundance of this electron. And here I'm showing other experiments. So this Bivlas is is a light by light scattering experiment. And so if there's a particle that is light and charged enough under RU1, then it would change the signal. And the fact that they don't see this light by light scattering puts a bound here. This astrophysical bound is from stellar cooling constraints. So if these particles exist, then stars would cool more quickly, and then you can exclude them. But again, this is slightly model dependent. So with some models you can evade these bounds. This future lab experiment is a Schwinger pair production experiment. So they proposed using a cavity with some strong electric field in it, and these particles are light and charged enough, then you will produce them, and then we will be able to detect them. Good.
Georges,
Yes.
isn't the current bound on epsilon to be it's around 10 to the minus 3?
Sorry.
How small can epsilon be? The mixing experimentally, do we know the bound on epsilon?
Oh, on epsilon. So yeah. So I guess it can be. So it depends on which epsilon. So if the photon is massless, then I don't think there's a bound unless you know that there is some other particle that exists. If the photon is massive, then I will show the bound later. I forget, but it's probably around there. Yeah, maybe around 10 to the minus. Yeah. So if the photon is massive, I will show it later. I don't remember the number, but I will tell you.
Okay, thank you.
Yeah, of course. Yeah. Any other questions? Yeah. Please interrupt because yeah, it's better to have a discussion. Okay. Good. So related to Gary's question, in the first bound, we were very agnostic about what epsilon is. We just assumed that epsilon is smaller than 1. But we can potentially get a better constraint if we know how big or small epsilon is. And so a natural question to ask is, what's the expected size of epsilon, either in string theory? And before we get to string theory, there's even an expectation in field theory. Because if we have a massive particle that is charged under R photon and the dark photon, then integrating this out produces a kinetic mixing operator with epsilon of this order. So it's proportional to the product of the two gauge couplings divided by a Young factor 16 pi squared. In string theory, the answer ends up being similar very often when it's not zero. And there has been a lot of work done on this, and in here I'll just mention one example. So, for example, in recent work that I completed with Aditya, we just look at a large number of heterotic orbifold models, and we compute this mixing parameter in them. And indeed, you can see that the mixing parameter here, the one standard deviation, is about 1%, which is the factor of 1 over 16 pi squared. So if we assume that epsilon actually has this value, then we can get a stronger constraint. And by going through the same logic, we can disfavor a region of parameter space that's above this green line. So this is a more aggressive constraint. Of course, this has an assumption built in that epsilon. So this region is not really excluded. But if you find something in this region, then you know that somehow epsilon, for some reason, is smaller than this. Good. Okay, so we have learned a few things about this dark electron, but then we can then ask what's really the spirit of Festina Lente. And the whole idea is that light charged particles in the sitter are inconsistent. because they can allow these black holes to decay into pathological spacetimes. They can allow large area black holes to decay into pathological spacetimes. And one example of a light charged particle are the gauge bosons of non-Abelian gauge theories. Okay, so these are exactly massless, and they are also charged. The gluons are charged under the gauge group itself. And so we can conclude from this that in the sitter, weakly coupled non-Abelian gauge fields are inconsistent with Festina Lente. So somehow all non-Abelian gauge fields must either be confined or Higgsed by the time we are in the sitter phase. Okay, both these possibilities are seen in our universe. So for example, in our universe, we have QCD, which is a non-Abelian theory, but it confines at 100 MeV, which is well above the onset of accelerated expansion. So this is well above the de Sitter phase that we live in today. And there's also an SU2 gauge group, but it stays at an even higher scale. So by the time we get to the de Sitter phase, there are no light charged particles left. So our universe arranges this in some very non-trivial way.
Should this be obvious? I remember I've talked to at least some of you about this at some point in the past, but these arguments about black holes decaying are about charged black holes.
Yeah.
If your black hole carries charge under the non-Abelian gauge field, then in the background outside the black hole, the gluons have a mass because they're coupling to the electric field of the black hole itself, right?
Right.
So does that, is it obvious that this is a problem and that it doesn't somehow fix itself through the interaction of the field with the background?
For these naive black holes, the mass is order h, right? For these big naive black holes, the mass is order h, so it's not enough that because h squared is smaller than m times h.
So people have actually worked out what is the decay rate of the electric field in this background. I think we talked about this after we talked about the paper. We actually worked out how this thing is still the case with it. So it's the mass is what George is saying. It's not high enough to suppress the exponential.
So just
Change
about
the-
it, so about it.
Yeah. Okay. There's another one factor.
Yeah, so the mass given by I don't know if yeah, so the mass given by non-Abelian fields is not enough to satisfy Festina Lente because it's order h. Yeah. Any other questions? Okay, so we then conclude from Festina Lente that somehow weakly coupled non-Abelian gauge fields have to be gone by the time we get into some decision phase, and this actually will rule out many phenomenologically interesting models, today and in the past during inflation. And just to showcase the applicability of this idea, I will just mention very briefly these three models. One which has to do with dark matter, one which has to do with dark energy, and one that has to do with inflation. But yeah, the details of the models are not the focus, but just that this idea can be applied to many models. The first one is a model where there's a non-Abelian gauge group in the dark sector, proposed in this paper in 2015. Now this is a very interesting model. There is a dark SUN, and dark matter is in the fundamental representation of this SUN. And for this, so which means that dark matter does interact with itself, and for this interaction not to be ruled out, the gauge coupling of this SUN has to be smaller than 10 to the minus 3. So this interaction would be ruled out, for example, by things like the Dirac cluster constraints. So this has to be less than 10 to the minus 3, which means that the energy scale at which this SUN confines is very low. It's e to the minus a million. Say in Planck unit. It's and so this SUN will never confine it. It won't confine today, or it won't confine in the near future. So within the next few V-folds, and so there will be always non-Abelian gauge fields that are present, like even when the universe enters, it's this third phase. And so this model is inconsistent with Festina Lente. Yeah, it has a number of appealing features that I will not go into. yeah, it has. There's another model. This is a model that attempts to solve the CC problem. So in this model, they have a phase of acceleration followed by contraction, and then you enter the Big Bang phase. And working out the details, the conclusion is that the Hubble parameter here at the end of the accelerated phase has to be ordered the Hubble parameter today. Otherwise, it's hard to say that this solves the CC problem. But for a Hubble parameter this low, we don't actually generate the fluctuations that we need for to see structure in our universe. And so they have to appeal to some other mechanism that generates these fluctuations. And the choice they make is warm inflation. So they couple this inflaton field to some non-Abelian gauge field that's weakly coupled, and the thermal fluctuations of that non-Abelian gauge field ends up generating the C's for structure. But again, this is a non-Abelian gauge field in the center, and that's weakly coupled, and so this mechanism cannot work. It might work if I mean this. I guess the mechanism itself might work, but the issue is the use of non-Abelian gauge fields. So if one can substitute that with some other system that generates these fluctuations, then it's okay. But the mechanism as proposed in this paper is at odds with Festina Lente. Yeah. Finally, there's chromonatural inflation, and so this is a popular model in which we have some axion field that is coupled to a non-Abelian gauge field, and this non-Abelian gauge field can take away some of the kinetic energy of the rolling axion, so that this axion can roll on a steeper potential. But then again, this model has non-Abelian gauge fields in the sitter phase, and
There's a background field configuration that exists.
Yes, that's also correct. This background field. So I have a slide actually on this.
Could you repeat Matt's question?
Yeah. So Matt is asking. There's a background field, and the background field Higgs is the gauge group, so that the gluons actually have mass in that, and is that mass enough to satisfy Festina Lente? But it's actually not enough. This is Matt's question basically. It's actually not enough because the energy density in inflation looks like this, and it has to be dominated by this term, which then means that this is much smaller than m blank h, and this is exactly the mass of the gluons. So asking that the axion dominates the energy density will imply that the mass of the gluons is too low to satisfy Festina Lente.
So the only way out is if the other term is dominant.
If this term is dominant, then it's radiation dominated. That it doesn't look like it's similar, and then yeah, right. Yeah, no, let's go back.
Sorry, what was psi
Does that
again?
answer the question?
Yeah.
Sorry, what was psi again?
Psi is the background gauge field. So the background gauge field A is A psi. Okay. Good. All right. And so these comments are more general. In particular, we should ask what happens to our standard model. So the vanilla picture of inflation looks like this. This here on the x-axis I'm showing time, and on the y-axis I'm showing temperature. And the usual picture we have is that there's some gut phase transition at a very high temperature, and this produces monopoles. But then inflation comes afterwards and dilutes the abundance of these monopoles, so we don't see them. At the end of inflation, we can reheat, and then we start the hot Big Bang picture. But the question to ask is whether there are standard model fields after this gut phase transition. Because like we said, this standard model has to be, the sv3 has to be either Higgs or confined, and the sv2 also has to be either Higgs or confined. And so somehow the gluons of the standard model have to be addressed. they somehow have to be massless during this inflationary phase. One way out for the SU2 for the electroweak SU2 is Higgs inflation. Perhaps if the value of the Higgs is large enough, then the mass of these gluons can remain very large during inflation, and so they don't pose a problem during this phase. For SU3, maybe one can do something similar with like some souped up version of Higgs inflation where you also Higgs the SU3. So there's no particular model that we have in mind, but this presents some opportunity for model building so I guess addressing this question. Okay, and this is the end of part 1. Any questions before we move on to other things?
Just a comment that
Yeah.
if you assume that at some scale the standard model is supersymmetrized.
Could you speak up?
Yeah, if you assume that at some scale the standard model is supersymmetrized, then potentially you can get very big doves along E-flat directions that break both SU3 and SU2. So
Right.
that's
So that's a model, yeah.
that's a scenario where you're not adding anything very exotic, you're adding
Right.
something kind of plausible and so.
Yes, thanks. Good. Okay, so now we'll start part 2, and so in part 2 we'll talk about photon masses, but like I said, I will first introduce a conjecture and then apply it, and then we'll see what we find. So in part 1 we have seen how the weak gravity conjecture and Festina Lente they constrain the masses of charged particles. But there's actually a different Swampland condition that can constrain the mass of the vector boson itself. Okay, and so in other words, we're going to be talking about massive dark photons this time, not massless dark photons. And so Gary, the answer to your question is about this 10 to the minus 7, I think, for massive dark photons. Epsilon, yeah. But for massive dark photons, again, these are very.
This is assuming they're dark matter, right?
This is assuming, sorry.
That bound that you're quoting, the 10 to the minus 7, assumes that dark photons are dark matter.
No, this one doesn't because this.
That one doesn't?
Yeah, because this one is from oscillations of the CMB photons to dark photons.
Okay.
Yeah.
The things below that, I guess, are all dark matter switches, but that one is.
Yes, these ones are such. Yeah, exactly.
Okay.
These are future experiments.
Okay.
Yes, thanks. Yeah, so dark photons, massive dark photons are again attractive phenomenologically. They can produce interactions in the dark sector. They can alleviate certain anomalies like Edger's 21 centimeter anomaly, as I will mention later. They can be the dark matter, as Matt was mentioning, and even though there's a mass here, this dark photon can still mix with our photon with the same mixing operator epsilon FF prime. And as you can see, there's a very large parameter space for these photons, and it's a very active area of research with many experiments being built to probe this parameter space. So these massive photons, they come in 2 types in effective field theory. They can be Higgs or they can have Stückelberg mass. Okay, so like I said, so the mass of the dark photon can come from the Higgs mechanism, in which case it looks like something like that, or it can come from a Stückelberg mechanism, in which case it looks it just has a mass term like this. And the difference between the two is that in the Higgs case, we restore the symmetry at high energy, and if we don't restore the symmetry at high energy, then we are in the Stückelberg case. Okay, we can perform the Stückelberg trick in here and reintroduce an axion so that this A has gauge invariance still. And we can do the same trick here and reintroduce non-Goldstone boson, but this is not important for this talk, so I will just ignore it and we'll focus on this axion. Okay, in other words, in this talk we're going to focus on the Stückelberg case for Stückelberg photons, and indeed these bounds that I showed are for the Stückelberg case, not for the Higgs case. Okay, so there are 2 conditions so now that we have an axion, we can use string theory to tell us more about the theory of Stückelberg dark photons. Because there's an axion, there's always also a radial mode, a saxion mode in string theory, and its mass is lighter than the mass of the photon divided by the gauge coupling G. There's also a UV cutoff on local QFT. So because there's an axion string, and this UV cutoff is basically the square root of the tension of that string. So that by the time we get to this energy scale, we'll produce these axion strings, and then local quantum field theory will break down these strings are instant objects. Good. So these are the two conditions we'll use here. So there's a saxion, it's mass bound above, and there's a UV cutoff. And the model we have in mind is this one. So first we had these two terms, and then we add the complication, which is just the mixing. And now we're adding one more complication, which is we're adding a mass to the dark photon. And good. So the first one that I'll talk about comes from the existence of the saxion, sigma. And because the saxion is a radial mode, this coupling exists in the Lagrangian, sigma dA squared. By gauge invariance, it actually has to look like this. Sigma A prime minus dA squared, which means that we have certain Feynman diagrams that are implied by this, by this operator. And in particular, there are Feynman diagrams that are very similar to the Feynman diagrams of the Higgs case. For example, this Feynman diagram exists. So in here we have our photon that oscillates into a dark photon, and then this coupling here between the longitudinal mode of the photon and the saxion. So this coupling here comes exactly from the cross term of these two. So it's sigma A prime dA. This process can cause stars to cool too quickly. So there are bounds on how important this process can be in stars, because this photon, it can be the photon in stars, and stellar cooling implies that this product, which is G prime times epsilon, has to be less than 10 to the minus 14. If it's bigger than this, then we should have observed stars cooling too fast. So any questions about this?
Yes,
Sorry.
can I ask
Yes.
again, like we have this, probably you have now a better intuition.
Yeah. Sorry, what's the question? I missed.
Hello?
Oh,
Yeah, we can hear you, Irene.
we can hear you.
Yeah, if you can explain again what is the intuition of what goes wrong if the saxion mass is too heavy, and if it's related also to the strings or not.
If the saxion mass is too heavy? Yeah, good. So this I guess Matt's the expert here, but I'll try. This combination here, Ma over G, is actually the decay constant F, is the axion decay constant F. And because there's an axion coupled to instantons, which in the effective action will produce, will produce terms that have some operator times e to the I, the axion over the axion decay constant F. So in the effective action, there's an operator that is e to the I A divided by F times some fermionic operator potentially. And then so this will give rise to Feynman diagrams that in which you can close the axion loops. So the two lines coming out from the operator, two axion lines, you can close them, and that will give some contribution that's lambda UV squared divided by F squared. It's quadratically divergent. There's only one propagator, and so this contribution will be quadratically divergent. It's lambda UV squared over F squared. So basically, lambda UV has to be smaller than F, and the claim is that this M sigma is what actually comes in the UV to fix that. But maybe there's a better explanation. Matt may have better intuition. I don't know.
don't know that I have a better explanation.
Okay.
I would say that the coupling you wrote down is not necessarily determined. So on your next
Right.
slide, I guess, that
Right.
one, yeah.
There's an alpha here, I would say. Like there's some constant here that we don't know.
There's some constant, right, and,
Yeah.
and the kinetic term can be canonical in such a way that you get their factors there.
So the kinetic term can be non-canonical.
I mean, so
Oh, this
like,
one.
like in the supersymmetric setting, this term just comes from expanding the Taylor potential for the
Yes.
field that contains this axion and the axion, right? And F squared comes from the second derivative, and this coupling you're writing down comes from some third derivative, and if things are non-canonical, then there could be a different factor in front. So I don't know how much I trust the exact number.
I see. I see. Okay, yeah, that's fair. I actually yeah, so that's fair. We actually did have a some number here, but then we removed it. But, yeah, but it's possible that yeah, it's degenerate to the gauge coupling. You see, so very small gauge coupling is the same thing as very small factor in some sense. At least for this.
Well, I think in general there's some freedom there. I mean, it's possible to check in some examples of what kinds of Taylor potentials fall out of reduced moduli and see what that factor looks like.
So that factor is really what's the metric in the model space, right? It's like how cylindrical is the but I think examples in string theory is always it's not crazy cylindrical. Right? It is related. So one way you could try to argue for something like this is like if you have something like a very cylindrical metric or a circle with an axion which has very sharp peak potential, you have an axion for which the d-2 global form symmetry is very close to being respected because you need to go over the top to break it. So maybe one can argue for a sharper version of this bound on this line, but we haven't done it.
Yes. Yeah. Also, so Erin, does that answer your question at least partially?
Yes, yes.
Okay. Good. Okay, so we have this Feynman diagram, which is the magnitude of which is bounded, and so this bound ends up. So a very similar diagram like to this is present in the Higgs case, and in fact in the Higgs case, there's a bound on the mixing, with the mass of the dark photon that looks like this. So the Stückelberg bound is up here, but then if there's that term that I showed you, then the bound goes down, so all the way here. And what we're saying is that the Stückelberg case is not actually very different from the Higgs case, in which case the bounds become something like this. So depending on how much, so in here, for example, this gauge coupling was assumed to be 0.1. Depending on how small our gauge coupling is, then regions above this line are ruled out. This in particular will rule out some interesting models. For example, there's a model here that attempts to explain the edges anomaly, the edges 21 centimeter anomaly, and it wasn't ruled out before, but now it seems to be consistent with this conjecture. Good. Any questions about this? Yeah, this is of course an interesting region. There's a lot of experiments. So if experiments detect something here, then we will learn a lot. Okay, we can also get another bound on the mixing epsilon, by assuming two things. So this time we'll use the second condition, that lambda uv is smaller, is bounded above by the tension of the axion string, and so we'll assume then that the tension of the axion string is somehow higher than the scales probed by the LHC. Otherwise, we would have seen it. And we'll also assume some one-loop kinetic mixing, and then we can get some bound on epsilon. This of course has a bunch of assumptions, so then I will just show the results. So if you assume these, then you get, then there's another constraint here which excludes this area of parameter space. Good. So that's all I have to say. I guess unless that, yeah, we can take questions later, but that's all I have to say. The quantum gravity imposes constraints on phenom models, and we have discussed here a few constraints on charged dark matter, on inflation, and the models of dark energy, and on photon masses, Stückelberg photon masses. Thank you all for listening, and yeah, if you have any questions.